All right, guys, hope everybody's doing okay. This is Mr. Karowski. We're going to take a look at something today called Factors Affecting Lattice Energy. It's a shorter lesson. It kind of builds off of and concludes the lesson on the Born-Haber cycle. And we're going to look at lattice energy, and we're going to see why is it larger for some compounds, some ionic compounds, than it is for others. Okay, so what are the factors that affect that? It's pretty simple, but it could be a little confusing because students get it mixed up with Coulomb's law and some other things we've learned about. So it's really important when we're looking at this, you have to make sure you know what you're focusing on, okay? So if you're focusing on lattice energy, really know what that means, okay? Lattice energy is when you have two ions coming together or you're breaking them apart, like that amount of energy that's taking place there, okay? If you're being asked about the Coulombic attraction between two atoms, okay, or I should say between one atom and its nucleus and the valence electrons of that atom, that's like a different set of things we need to look at. Okay, so let's get into it and then we'll talk about it. So you already know this, but again, lattice energy is the energy required to split apart the ions in an ionic compound. Now, when we did the Born-Haber cycle, we were bringing them together, okay? But if you want to take them apart, that's also the lattice energy. But if you are splitting them apart, that's the energy that's required. Well, that's going to be a positive endothermic value. It's also defined as the energy released when the ions come together. That's how we use it in the Born-Haber cycle. That's a negative exothermic delta H value, right? So here, for the positive delta H value, it's found on the reactant side, and it's on the product side here, if it's the negative delta H value. Because of the very large lattice energy, the overall energy of formation for ionic compounds is always exothermic, right? So we saw that in the previous lesson on the Born-Haber cycle. So lattice energy, big time exothermic value. So the overall lattice energy, or I'm sorry, the overall energy of formation is going to be exothermic as well. Okay? So here's our formation equation for lithium fluoride. Li plus 1/2 F2 yields LiF, and our delta H, negative 591. Okay, so that makes perfect sense. The delta HF, delta is change in, H is energy, and the F means formation. So the heat of formation or energy of formation here. That little degree sign actually means at standard conditions. We'll talk about that in our thermodynamics unit. So here's a chart of lattice energy. What patterns do you see, and how can you explain them? What you want to do is just try to see some trends here. So I'm looking at a couple things that jump out to me. I see that there's some big numbers here for aluminum, way bigger than these. I also see a huge number over here. So like aluminum fluoride, it's 5,215 for the lattice energy. So when aluminum fluoride is created, it releases 5,215 kilojoules per mole. But when aluminum oxide is created, it releases 15,916. It's a big difference, okay? Well, what's the difference between aluminum fluoride and aluminum oxide? Well, the aluminum part's the same, but the anion is different. Well, the F-1 ion contributes to the 5,215, where the O-2, a negative 2 charge versus a negative 1, gives us 15,916. All right, so that could be something to do with it here. So difference in charges looks like it has something to do with this. And then what else could make a difference? Let's look at lithium fluoride, 1,036. Lithium chloride, 853. Lithium bromide, 807. Lithium iodide, 757. Lithium oxide, that's almost 3,000, 2925. So there we go again. So we have Li plus 1, negative 1, negative 1, negative 1, negative 1, negative 2, big jump. Charge, definitely an impact. But the charge here is all the same. -1, -1, -1, -1. What's different here then? The size is different. Okay, fluorine is in level 2, chlorine's in level 3, bromine level 4, iodine level 5. Okay, so it looks like as our size differs, so does the lattice energy. So let's try to summarize this into some simple trends. Okay, so here are your factors that affect the lattice energy. So again, we're only focusing on lattice energy here, and not some other trends. Okay, so it can be a little confusing, but I'll try to summarize it for you. One of the factors that affects the lattice energy, which we looked at, is the amount of charge. What we saw in that previous chart, higher the charge, like the O2, O-2, I should say, that contributed to a larger lattice energy. So higher charge means higher attraction. NaCl, the lattice energy is 788. Na2O, so we have, Na is the +1, right? Cl is a -1. O is a -2. Okay? Big time difference in lattice energy. Look at that. Because the Na is a +1 and the O is a -2, there's an opposites attract, right? There's so much more attraction between a -1 and a -2 compared to a -1 with another -1. All right? I mean, clearly there's some attraction here with NaCl, but there's just way more of it because of your difference in charge. Okay? So you always want to look at your magnitude of charge. The larger that is, the bigger your lattice energy is going to be. Something else to look at, which is what we looked at on that chart, is the size of your atom. Smaller atoms have a higher attraction. Okay? Lithium bromide, 787. Lithium chloride, 828. So which one's more important? Let's look at this one more time. The size of atoms. Why do smaller atoms have a higher attraction? Well, this kind of goes back to Coulombic attraction, where your smaller atom had a higher attraction to the valence electrons, okay, because they were closer to the nucleus. It works the same way here. Lithium is in level 2, so it's the same for both of these. So we have lithium here and lithium here. Here is bonding to bromide, okay? Bromide is in level 4. Okay, so here's bromide. I'm summarizing this here. This is not going to be very neat. Here is bromide in level 4. Okay. So lithium +1 is attracted to the bromide -1. Opposites attract, obviously. So some attraction here. Lithium could only get so close to the bromide because its electrons are in level 4, right? Lithium chloride, though, chloride is in level 3. Okay, so here's chloride, -1, lithium +1. Okay, here's chloride in level 3. Okay, not the greatest circle there. In which situation here can the two ions be closer together? Well, obviously, this case, right? Chloride ion only has 3 levels, so lithium could be as close as that 3rd level, theoretically, right? Bromide is with level 4, so lithium could only be within 4 levels, theoretically, of the other ion, right? So because they're further away here, the attraction is less. The lattice energy is less, 787. Here, closer together, 828. Now, not a huge difference there, right? Look at the big difference here. Difference in charge, look at that, 788 to 2570. Here, you're talking less than 100 kilojoules per mole. So which of the two is more important? That goes back to this trend here. You can see that the magnitude of charge is. So huge big idea here. Magnitude of charge is the most important factor. The radius, level 3 for chloride, level 4 for bromide, you're still talking about atoms, and ions. They're super, super small. So yes, the radius is different. The energy levels are different, but it's not that different. Like, it's not going to contribute too much, really, in terms of size. The charge outweighs that big time. Okay? This is for lattice energy. So remember that. Please don't get this mixed up with Coulomb's law, where the trend is, part of this is opposite. Remember, for Coulomb's law, when we looked at attraction of nucleus to valence electrons, okay? Again, nucleus to valence electrons, the most important thing was energy levels, okay? If I said, which one's more important here for this, like shielding, or I should say, nuclear charge, like number of protons, or the size of the atom, the number of energy levels for chloride and bromide. Well, it's definitely the number of energy levels, right? Bromide's in level 4, chloride's in level 3. We're not talking about that here, okay? So Coulomb's law focuses on, remember our priority list? Number 1 was number of energy levels, okay? That was it, number 1 factor for Coulomb's law with nucleus to valence electrons. Here, that's not the more important factor, okay? It's the second factor. Charge is what outweighs that here, because we're focusing on something different, right? We're creating ionic compounds here. So ionic compounds are formed because of attraction of positive and negative, okay? So don't get this mixed up with our trend we reviewed earlier when we compared one element to another element. You compared chlorine to bromine, right? Attraction of valence to nucleus. We had our priority list. You need to know that priority list for Coulomb's law when we talk about valence electrons to nucleus attraction, okay? When we talk about lattice energy, we focus on magnitude of charge first. We're looking at the attraction of one ion to another ion here. So again, there's 2 different priority lists for 2 different things. It's up to you to keep them organized and straight, okay? If you just think about it, again, don't try to overanalyze all this. If you think about what is lattice energy, well, it's an attraction of ions. And okay, what's going to make that, how is that going to change then? What's going to impact that the most? Well, if it's an attraction of ions, ions have charges that are opposite, right? Well, then you should focus on that attraction of opposite charges, and the charges themselves having the biggest impact there would make sense. So I'm trying to help you guys think through this process here. So you don't try to just memorize a million things. Think a little bit, it'll all come together, and you have to memorize less. Okay? Remember, know a little bit of stuff really well versus a lot of stuff not so well. Last thing, predict the effect lattice energy would have on the melting point. Okay, so here's some extension of this. Melting point, you're going from a solid to a liquid, right? Well, if you have a very strong lattice energy, a very strong attraction between your ions, then it's going to be, pretty difficult to melt that, right? So the higher your lattice energy is, the higher your melting point is going to be, because it's going to take more and more energy to break that attraction between parts of that compound and turn them into the liquid state, where there's less attraction compared to the solid state, right? So if you have something with a lower lattice energy, it's the attraction isn't as strong, then it's going to take less energy to melt that. So here you go. You have 5 compounds here. Match each one with the melting point. So what you want to do is look at all 5 of these and figure out which one has the highest lattice energy. Go from highest to lowest there. Then compare melting points and kind of match them up. Okay? So take a second and do that. Pause the video and then see if you got it right. Okay. So here's the strategy for this, guys. Go through and find your magnitude of charge on all these things. So K is a +1, Cl -1. K plus 1, I minus 1. Mg plus 2, O minus 2. K plus 1, Br minus 1. Sr plus 2, Cl minus 1. Okay, here we go. What is the number one most important factor when looking at lattice energy? It is magnitude of charge. So right away, I look at number 3. Okay, it's a plus 2 minus 2. What else is even close to that? Well, number 5 is plus 2 minus 1, but here you have a 2 and a 1, here you have a 2 and a 2. So right off the bat, that tells me MgO has the highest lattice energy here, and therefore the highest melting point. Okay, so that's going to be letter A, 2800 Celsius. What's the next highest lattice energy? Well, 1, 2, and 3 are all 1, 1, 1, 1, 1, 1. 1, 2, and 4. Number 5 is a 2 and a 1. So number 5 is the next one. Okay, 874. So magnitude of charge is basically done now. Okay, because everything else is a tie. Magnitude of charge is a tie. When that's a tie, you go to your tiebreaker. So you have 1, 1, 1, 1, 1, 1. Tiebreaker is size. Potassium, 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 all the same. You're looking at Cl, Br, and I. Okay, look at your periodic table. Chlorine, level 3. Iodine, level 5. Bromine, level 4. Okay, what's your trend then? Potassium is bonding to these other ions, right? The stronger attraction, therefore the higher lattice energy, is when potassium can get as close as possible to that other ion. So look at number 1, KCl. Potassium can get to within the 3rd level of the nucleus there. For potassium iodide, 5th level. Potassium bromide, 4th level. So KCl is the next highest lattice energy because the stronger attraction, okay, between the two. K gets closer to Cl than it does with Ki or Kbr. So we're going to have 772 for KCl. Then Kbr is the next highest, 735. And then finally 680 for the last one. Okay? Magnitude of charge first, and then size second. The closer the ions get together, the stronger the attraction, the higher the lattice energy, the higher the melting point. Therefore, the smaller size allows that to occur. Okay, guys, that takes care of it. So this kind of wraps up the ionic compound portion of this, and we'll move forward with looking at covalent molecules going forward, seeing how that works, really for a big chunk of the rest of this unit. Okay, hope this made sense to you guys, and that's it for today. Thanks a lot.